Okay, we're ready for Notes 11A for the Math 4 course. We're going to be talking about vectors today. And at some level, vectors are basically arrows. um, Arrows that serve two purposes. One, they indicate direction. Direction is important with a vector. And the other thing is that there is some element of magnitude, is the proper term. Basically, how big, how long, how important, whatever. Um, Most of the time, you wind up using vectors in things like physics, where you're talking about, let's say that there is a box, a very heavy box sitting on the ground, and it's got a handle on one side with a rope, and you're pulling that way. And it's got a handle over here with a rope, and somebody's pulling that way. Well, the thing is that if somebody's pulling up, somebody's pulling that way, it's eventually going to travel in that direction. And so vectors allow us to, with the use of the arrows, so to speak, we're able to not only talk about what direction that the force is being used, but also the magnitude of the force. Like I remember being in a physics class and doing lots of vector equations involved in different kinds of force. And of course, force is more than just, pounds. Uh, Force can be, how much, uh, you know, force that you're using on something. It can be velocity, it can be acceleration, it could be a number of these things. But basically, we're talking about a vector as a quantity that has both magnitude or size and direction. Now, what I've been calling an arrow, I guess the proper term is a directed line segment. It has direction. It's starting from P and going to Q. Now, P would be described as the initial point or tail, and then Q would be described as the terminal. Now, terminate means to stop or to end something. Terminal point is where it ends. Now, we could describe it as vector PQ. And there's also that little lowercase p that we can do that with it and describe it as vector p. As sometimes they will even take the lowercase p, but they will bold it and refer to it that way. So you'll see kind of a mix and match of all three. Now, that is a website we'll come back to in a little bit. There's also the issue of what it was tough to think about. A zero vector has a magnitude of 0. Well, if it starts at this point and it's going nowhere, then it's going to end at that point too. And so I guess you could say a 0 vector is nothing much more than a point. It's both its beginning and its end at the same point because it's not going anywhere. So anyway, all right. Now, if they give you an ordered pair for the initial point and the terminal point, this gives us the ability to plug it into the distance formula and figure out the magnitude, how long it is. Well, that's the distance from this point to that point. It kind of makes sense. So the double lines there, this is not just absolute value. This is the magnitude of V, which basically is saying that, this is how strong it is in that direction. All right, so let's find the magnitude. We're going to plug it in, and I always like to go through and label this stuff because it is so much easier to plug in when you're just looking at, there's x sub 2, there's x sub 1, square that. There's y sub 2 minus y sub 1, square that. So we wind up with negative 15 squared, and that's like negative 2 plus 4, which would be a positive 2. Square that. we get 225 plus 4, which is going to be square root of 229. Now, if square root of 225 is 15, then we know that square root of 229 is just barely over 15, like 15.1 or something like that. I am okay with leaving it as the square root like that because they didn't specify how to leave your answer. I told the story in class about how it's kind of like the guy that I don't know if he quit or got fired or whatever, but the boss owed him $900 on his last paycheck. And he kept harassing the boss to, give him his pay. And finally, the boss did. He dumped $900 worth of pennies soaked in motor oil on the man's driveway and put his check stub on top of that and a very unpleasant note. But anyway, bottom line is that he still paid him with legal tender. Even though it was an inconvenient way to pay him, it was still legal. He legally paid him $900, so he had lived up to his end of the bargain. So here, yeah, if you put 15.1 yada yada yada, you're rounding at some point, which means it's not an exact answer. And I personally have a preference for exact answers because nothing is left behind with that answer. You got it all right there, square root of 229. All right, let's move on. X sub 1, y sub 1, x sub 2, y sub 2, and we're going to plug in and have 5 minus negative 3, square that. 6 minus 10, square that. So that should give us 8 squared plus negative 4 squared, which is going to be 64 plus 16, which is square root of 80, which is just under square root of 81. Square root of 81, of course, is 9. So, this answer is going to be a little less than 9. And I'm okay with the square root. Okay. Let's try another one. Now, I will say that normally when I'm teaching the distance formula to like Math 1 students, I will comment on the fact that technically it doesn't matter whether you say x sub 2 minus x sub 1 or x sub 1 minus x sub 2, just as long as you're consistent in both parentheses. But I'm not going to push that here because there are some other elements involved in vectors where order is critical. And so I'm not going to push that issue because I'm afraid it's going to hurt more than it's going to help. All right, so we're going to say 2 minus negative 8, square that. Negative 9 minus 6, square that. That should give me a 10 squared plus negative 15 squared, which is going to be 100 plus 225. And as it turns out, the square root of 324 is exactly 18. So we know this is like 18.0 something. It's barely over 18. But that is the exact magnitude of this vector. And then the last one. Okay, so we'll say negative 6 minus negative 1. A lot of negatives in this one. Just about everything has a negative sign to it. We're going to have to watch our signs. That's negative 6 plus 1. That's going to be negative 7 plus 5, which is going to give us 25 and a 4, square root of 29. Okay. Now, when we move on to the next section here, one thing that's going to be a real important is the term component form, and that's what it's going to look like. Basically, in order to do my vector, it tells me how much to move on x and how much to move on y. Now, the thing we have to be careful is that this is not an ordered pair like X and Y. This is an ordered pair, and it gives me a location. That's a location. When it's rounded parentheses like that, it's a location. But when they're pointing brackets like this, this indicates direction. All right, this says that I'm going to go so many units on X and so many units on B, and then I'm going to land where I need to land. All right, now something to notice here is that this looks very much like the stuff that was inside of the distance formula, and you would be right. But it is important to notice the order here. Here, because they're not being squared, this means that order is critical. All right, you are only playing with one vector here, and order is important. All right, so let's try this with a couple of them. Now, I haven't done this yet. If we were to start at the origin, and the component form was vector A and then B, then A and B would be my finishing point, my terminal point, because the origin would be where this is starting from. Now, sometimes it's nice and convenient that way, and sometimes they give you an initial and a terminal, which neither one of them are the origin. So let's play with some of those. All right, again, x sub 1, y sub 1, x sub 2, y sub 2, and our vector, our component form of the vector, is going to be 6 minus 3 and 3 minus 5, which means 3 and negative 2. Now what this is saying is that if I were to go from C to D in that direction, in that order, I'm going to go 3 units to the right and down 2, and I should land there. And that's where my vector is going to take me from C to D. Let's try it with this guy. So negative 2 minus 5 and 1 minus 10, which says if I want to go from R to S, I need to go 7 units to the left and 9 units down. And that is the direction and the magnitude. Well, I don't have a magnitude. I'd have to do like 7 squared plus 9 squared and take the square root of that. But it is involved in the distance formula. All right, let's move on to this. I guess this is where I need to open up that website that was earlier in the notes. Okay, we're going to go to the link from GeoGebra. And I would start by describing the U in green and the V in red. Let's kind of start there. The best mental picture that I can come up with is that you have got someone trying to swim across a river, and they are swimming in one direction, but the current is pulling them sideways. It's kind of like they're trying to go across the river at a 90-degree angle, but so this person is swimming as hard as they can in that direction, but the current is pulling them over here. So by the time that you consider both forces at the same time, you get this guy right here, U plus V. All right, and this is when we start looking at adding vectors together or subtracting them. This is literally what's happening. Now, what would happen if I started with the U? Oops. If I started with the U, and instead of going forwards with V, I go backwards. Look at the direction that you're going now from U minus V is going to be like this guy right here. okay? Notice whatever V is doing, if I go back the other way, that's negative V. And even if I only go halfway, half the distance, however long this is, this represents half of V going the other way, negative 1/2 V. Now I can play this game if I decide to start from V and go up V and then go backwards on U, V minus U. I'm going forwards on V, but I'm going backwards on U. Now notice that these guys are parallel to each other. U minus V and V minus U. It's a question of what direction are you going in? You going up or down? All right. So that's that's as much as I'll play with that for right now. There is that idea of tip to tail, tip to tail. When you are trying to consider the effect of two vectors or more, you kind of arrange them tip to tail. This reminds me of, and I'll go back here. This reminds me of one of those questions where Egbert walks 10 miles north and then turns and walks 5 miles east. How far is he going back to the original starting point? And that's very much what's going on here, is that if I am pushing along that vector and something else is pushing me in that, then this is the direction. It's like a plane is trying to go in that direction. There's this really strong wind that's pushing him that way. This is going to be the actual flight path of the plane. So now, you're seeing this in triangle form, so you can understand the idea that, especially, well, you think about it, planes get their directions in terms of the 360-degree compass, right? So, I'm setting a heading of 90, which means that he's going east, due east. And he's got a certain speed, and the wind has a certain speed, and this is how you calculate the actual flight path of the plane, is that, he may be setting, his direction in that direction, but the wind is blowing him over here. And so remember the law of sines and law of cosines, where we could take an oddball triangle like this, and if we knew some of the pieces, we could find things like, what was the angle of that guy right there? Now, if you're a pilot in a plane, you're going to need to know these kind of angles. So I'm not sure if we're going to get to that in this course, or whether we'll leave that to something like pre-calculus. I got to look at our next section and find out just how far we're going with this. All right, this would be kind of the, we decide we're going to go in the direction of V, but then we're going backwards on W. That's V minus W. And so if we do that, this is our actual flight path, so to speak. And the thing that's going to become important here is these formulas here are very order specific. Order is important. And the other thing I want to point out is that there are two vectors here, not just one. Now notice that here with two vectors, it is a sub 1 minus a sub 2. Oh, wait a minute, back up here. When we were borrowing from the distance formula, it was x sub 2 minus x sub 1. It's like it was kind of backwards in order, but over here, they are forwards. All right, when you're adding and subtracting vectors, it is important what order you are doing it in. And so you do not switch the 2's and the 1's on these guys. All right, so what's going to wind up happening? All right, let's say we're going to add A and B. We're going to take A, and he's got a -6 there and a 1 there. And he's got a 2 and a 7. And that we're going to do it exactly in that order, in the order that they gave it to us. Now, the thing is that by the time I, follow whatever A is saying I should go 6 left and up 2, and B is saying I should go right 1 and up 7. And so by the time I get through doing both of these tip to tail, I've actually gone left 5 and up 9 altogether. That's that dotted line that's showing the combination of the two of these. All right, let's try this one. And again, it is important that we do this in order. So we're going to have -4 minus 1, and then we're going to have 5 minus 7. So that's going to be a -5. That's going to be a -2. So by the time that we do C and then we backtrack on B, we might as well have gone 5 to the left and down 2. So remember, with these, when you are doing more than one vector, order is important. When you are doing only one vector, you can probably do the x sub 2 minus x sub 1 and have the order be seemingly backwards and still have the right answer.